All right, everyone, please take your seats again for the next session, the last session of the day, about garbled circuits. We'll wait just a moment for people to come in, and could someone close the door, please? That would be amazing. Thank you very much. Okay. Yeah, welcome to the garbled circuit session. We have a first talk about bit GC, garbled circuits with 1 bit per gate, and you is going to give the talk. Thank you.
Good morning. I'm going to present this bit GC with 1 bit of communication per gate. This is joint work with Hanlin Liu, Xiao Wang, and Kang Yang. First of all, we briefly review what is garbled circuit. It is an essential tool for enabling two-party computation in constant runs. And the garbler prepares the circuit and sends the garbled version to the evaluator. And then the evaluator evaluates the circuit, the garbled circuit, with the garbled input to produce the garbled output. And here we have 4 algorithms: garble, encode, evaluation, decode, and there's essentially a couple of guarantees, such as correctness. So the garbled circuit should compute the same function as the original circuit. And this computation should not leak nothing substantial beyond the output. So we typically use simulation-based definition. There exist efficient simulators such that the simulated view is computationally close to the real view. And in addition to constant round secure two-party computation, we also have, which was the garbled circuit was invented for. We also have other applications such as zero-knowledge proofs, identity-based encryption. So the ability to securely compute the circuit without revealing the secrets make it essential for many security-relevant applications. And in the world of Eurocrypt, where only symmetric key cryptography is possible, the garbling typically takes linear. The cost per gate is linear in the security parameter, which is lambda, the bit length of the wire table label. Okay, so despite various improvements such as free XOR, half gate, 3 halves, we still have this linear in lambda bits per gate cost. And with symmetric primitives, the garbling can be very efficient. So taking the example of garbling an AES circuit, and it used to take seconds, but now it can be completed within 1 millisecond, and by using hardware optimizations such as AES new instruction set. So it's quite practical. And another line of research focuses on make garbling succinct or even reusable. So the communication will be very little, but to typically rely on very computational expensive tools like indistinguishable obfuscation or FHE, and sometimes some even use very strong assumptions like multilinear maps. So they are not practical yet. To summarize, the garbling in Eurocrypt can be very efficient, but the communication is linear in the security parameter. And on the other hand, the fancy constructions, they only need very little communication, but they are not, the computation is not realistic yet. So it's quite natural to ask, is there a middle ground where we can have efficient garbling, small communication, yet still using very moderate assumptions? So this is the motivation of our work. So we use moderate assumptions, like lattice assumption with circular security. So this is the same assumption used by FHE, but unlike FHE, which needs to bootstrap, we don't use bootstrapping. We only the garbling is very efficient. Per gate, we only use a constant number of homomorphic operations. Okay. But we use this circular security for another reason, which I will tell you later. And the communication, we reduced the communication from linear cost to the constant, which is a single bit. And concretely, we use ring LWE with circular security as the assumption. And we use a special, somewhat homomorphic encryption, which we only need like a constant number of polynomial ring operations per gate. And the communication size is single bit per gate, as I said in the title. Okay. Before presenting the scheme, I want to take a step back and try to explain, understand why the communication is large for this classical GC. So because in the garbled table, the output labels, they are encrypted under the key of the corresponding input labels. And for each while, the label, one of the label is random, the other is random string XORed with the global key. So at least one of the label, they have the full entropy. So it's harder to compress even in the sense of information theoretical sense, right? Okay, so our scheme tried to think from another perspective, from the perspective of secret sharing. So the Garbling evaluator, at the beginning, they have the shares of the input bit times the global key, right? This is like a secret sharing-based two-party computation. And then instead of sending over the garbled or the encrypted truth table, we divided this truth table, the encrypted truth table, into two parts. The first one is the encrypted random bits. And these random bits are produced from a PRG. And the other part is the difference is the so-called difference bit, which is the wire masks further XORed with these random bits from the PRG. Okay. And so with these two parts, we can efficiently reconstruct the truth table, the encrypted truth table. And the communication for the first part is very, very succinct, thanks to the use of homomorphic encryption. So we only need to send the encrypted seed rather than the encrypted PRG output. And the second part is 1 bit per gate, so which is the main communication. Okay. Then both parties, they can just do the evaluation locally with no communication to produce the output bit, the shares of the output bit times this global key. Okay. So to achieve the task, we need a special, somewhat homomorphic encryption that can evaluate up to a certain depth. And this depth is essentially the depth of the PRG plus 2. Okay, and this PRG, in practice, we should instantiate this PRG with a low depth, like low depth PRGs that can be implemented using very shallow circuit. Okay. And our decryption is very special. So the ciphertext of M decrypts not to M, but to M times delta. So this is where we need this so-called circular security assumption, right? Because the message is actually depending on the decryption key. So our evaluation function has this property we call distributed evaluation. So the difference between what the evaluator evaluates and what the Garbling evaluates will equals to like a few weighted sum of the plain text, where this ij are the indexes of the wire labels, input wire labels. And this evaluation function also satisfies this so-called ordinance property, saying that if we negate the ciphertext, we also get the negative evaluation result. Okay, so in order to support homomorphic encryption, we have to use polynomial rings as wire labels instead of the traditional bit streams. And here are a few key differences. So the notations, they are the same, but before we use like the first bit of the global key is set to 1, and now we set the first coefficient of the global key to 1, right? And the permutation bit equals to the first bit of the 0 label, and now it equals to the first coefficient of the 0 label modulo 2, right? And before, the 1 label equals to the 0 label XORed with the global key, and now it's like the A1 equals to A0 plus or minus delta. And this plus or minus depends on the value of the permutation bit, right? So These are the differences. And then if we take a closer look and see how the garbler and evaluator, they compute, the garbler and evaluates a single gate. At the beginning, the garbler will have, for each input wire, it has 2 labels, right? But the evaluator only have, for each wire, input wire, it has only 1 label, which corresponding to the input bit, right? And then they invoke this homomorphic evaluation, the homomorphic evaluation of this somewhat FHE to get the encryptions of the truth table we call tidal tau. And then by taking the invoke the evaluation function and then taking the least significant bit, we get the permutation bit of the output, by using the ordinance property. But here, many details are omitted. And then it stands this difference bit, which is the permutation bit further XORed with this random bit RC. And then, using this difference bit, they further negate the ciphertext of the truth table. And then both parties, they can just invoke the evaluation function so that the garbler will get the 2 labels for the output wire. But the evaluator only gets the 1 label that corresponding to the output bit. And they both get the ciphertext for the random bit, for the permutation bit, pi c. Right. And in terms of cost, so the garbler, the evaluator, will both use the homomorphic evaluation function, homomorphic evaluates a circuit of depth 2 to get the corresponding encrypted ciphertext. Right? And they both invoke the evaluation function a constant number of times. Oh, that's pretty the computation cost. And as for the communication cost, it can be very succinct. As I said, we just need to send the encrypted random seed so that whose size can be basically omitted. And then the evaluator can homomorphically evaluate the PRG to get the encrypted random bits. Right. Okay, so this is our work called BitGC, and we also extend to we also have a follow-up work we call authenticated BitGC, where we extend this passive security to active security against malicious malicious adversaries by paying twice overhead in both communication and computation. And compared with the previous state of the art, the communication is reduced by 2 orders of magnitude. So this follow-up work will appear at this year's crypto. Okay, that's my talk. Thank you very much.
Okay, thank you very much. Do we have any questions? Now is your chance. No questions? Okay, then let's thank the speaker again.
Thank you.
And I will ask the second speaker to come up. Yes. Where's my program? Okay. Our second speaker is Aditya, and is going to tell us about breaking the 1/lambda rate barrier for arithmetic garbling.
Thank you. Hello, everyone. I'll be presenting breaking the 1/lambda rate barrier for arithmetic garbling. This is joint work with Jofa, Karmeet, and Naman. So let's get started. So I'm sure you all know what garbled circuits are, but just let's quickly recap. So a garbling scheme allows a garbler to take a Boolean circuit and compute an encrypted circuit called a garbled circuit and some key. The key can then be used to encode the input, and an evaluator can then use the garbled circuit and evaluate it on the encoded input. The correctness property guarantees that the output of this evaluation is equal to the Boolean circuit's output on the original input. And the key property that we want from garbled circuit is the privacy property, which guarantees that the garbled circuit and the encoded input reveal nothing beyond the circuit output. In this work, our focus is on garbling arithmetic circuits, where computation occurs over some ring R. So how do we garble such circuits? Well, garbling schemes allow garbling Boolean circuits. So one straightforward approach is let's replace the ring operations with their Boolean circuits representations, and then let's garble the resulting Boolean circuit. But the resulting Boolean circuit is large because we're making non-black box use of the underlying ring operations. For example, if you just consider integer arithmetic, then each integer operation requires, over L bit integers, requires L log lambda log L Boolean operations. So even with like 32-bit integers, you have a 160 times overhead in the size of the Boolean circuit. And the other issue is that to evaluate the resulting garbled circuit, you really need an encoding of the bits of the input. And in some applications, like in cryptography, where we use garbled circuits, it's not possible to do this bit decomposition of the inputs. So we really want to directly work over the ring R. And this is precisely why Applebaum, Ishai, and Kushelowitz posed the question of arithmetic garbling, which asks if we can directly garble the arithmetic circuit without Booleanizing it first. And in their paper, they give a positive answer. And before we continue, it would be helpful to have a measure of efficiency of garbling schemes, because at its core, arithmetic garbling is about efficiency. We want to do it better than Boolean garbling. And a standard measure of efficiency that's been used in the literature is known as the rate of the garbling scheme, which is basically the ratio of the size of the arithmetic circuit, which is the number of gates in the circuit, times the number of bits required to represent each element of the ring, to the size of the garbled circuit itself. Roughly, what we are saying is how much the ratio of the bits required to write down every wire in the circuit to the size of the garbled circuit, and that's the rate. And higher the rate, the more efficient the garbling scheme. So arithmetic garbling has been studied in two regimes in the literature. The first is bounded integer arithmetic, where we compute over integers, but we require that all intermediate values are less than some magnitude bound b. And the other is standard modular arithmetic, where we compute over an integer ring ZB. In the bounded integer setting, recent works have shown how to get rate 1 arithmetic garbling. Essentially, the garbled circuit has no overhead compared to writing down all the values in the circuit. On the other hand, in the modular arithmetic setting, all the best-known works have a rate of 1 over lambda. So there is a significant blow-up in the size of the garbled circuit. And the main question we ask in this work is if we can break this 1 over lambda rate barrier and get more efficient arithmetic garbling schemes. And we show that we can do this. So we construct an arithmetic garbling scheme for polynomial-sized integer rings, ZB, where the rate is log b over lambda. And we construct the garbling scheme assuming parDDH and the existence of tweakable correlation hash functions. Tweakable correlation robust hash functions are an extension of correlation robust hash functions, which are used in garbling schemes, most of the garbling schemes. And what they ensure is hashing correlated inputs maps to pseudorandom values. And it's somewhat assumed to be like a minimal assumption on symmetric key primitives. So going back to the previous picture, what we get is, since b is polynomial in lambda, what we essentially get is a log lambda improvement in the rate compared to prior works. And a key component of our construction that leads to our results is a new parDDH-based puncturable PRF, which has some nice properties. It has it breaks the key into two parts: a public reusable setup, and each PRF key itself is just a single element. It's a single exponent. And the fact that the PRF key is small is actually what lends us the rate, is one of the factors that lends us the improved rate. It has also a few other properties which make it very good for garbling, which I'll get to later. So in the time that I have left, I'll go over how we actually I'll go over the details of our garbling scheme. Okay, so our starting point is a template that's been used by most of the garbling schemes in the literature. Turns out most of the garbling schemes in the literature essentially require the garbler and evaluator to perform a secret shared evaluation of the circuit. So what do I mean by this? The encodings of the inputs are essentially secret shares, additive shares of the inputs. And then the garbler and evaluator perform a gate-by-gate evaluation of the circuit to ensure the invariant, that they have additive shares of every intermediate value. To maintain this invariant, the garbler generates garbled material, which is then used by the evaluator to maintain the invariant on their end. So now the main question is, how do we maintain this invariant? And most of the garbling schemes rely on what is known as a multiplication gadget, or what I'm calling here as a multiplication gadget, which essentially takes a value from the garbler x, a value y from the evaluator, and outputs shares of their product. And what we want is to realize this primitive with a single message communicated from the garbler to the evaluator, and this message can then later be included in the garbled circuit. But turns out to have this single message, we need the parties to have some correlated inputs. The garbler, essentially, they should have shares of delta times the evaluator's input, where delta is known to the garbler. And this delta is common across all invocations of the multiplication gadget. And looking ahead, when we actually use this gadget for garbling, this y will correspond to the evaluator's share. So now we need a modified invariant to use this multiplication gadget. We need additive shares of every intermediate value, as well as the garbler has a key and the evaluator has a label, which are shares of delta times the evaluator's share. And using this, we can keep using the multiplication gadget to maintain the invariant. Okay, so we want to use this template for constructing garbling to construct modular arithmetic garbling schemes. But now we need to be a bit more specific about the space over which these shares live. So we want the first set of shares, the shares of the secret, to be mod B, because we're computing a circuit mod B. But the second set of shares are dictated, the modulus for that is dictated by the multiplication gadget. And it's not in our control because the multiplication gadget might use cryptography, so it's a different modulus, P. And this modulus mismatch actually makes it very hard to maintain the invariant in the modular arithmetic setting. So let me demonstrate this with a simple example. Say parties have their keys and shares, the keys, labels, and shares for input wires of an addition gate, and they want to maintain this invariant for the output wire. So one very straightforward approach, because shares are linear, is the parties simply add up their shares. Now, as we'd expect, because shares are linear, the G3 and E3, which are the shares of the garbler and evaluator, they sum up to the sum of the secrets, or the input values, which is good. So we've maintained the first invariant. But the second invariant, when we add K3 and L3 mod P, what we get is delta times E1 plus E2 mod P. But this is not what we want, because the evaluator share is E1 plus E2 mod B, and and we want this mod B mod P. So we want to really compute over two moduli, and simply adding the shares does not do this. So one of the key observations we make in our work is actually a small twist to this multiplication gadget suffices to regain, to make things go through. So we have the multiplication gadget on our left, which we just saw. And what we need is what I'm going to call as a transform and multiply gadget. So it has the same inputs as the multiplication gadget, but it outputs shares of x times f of y at f, where f is some function, and this f is like a transformation function on the evaluator's input. And we show how to construct this transform and multiply gadget for any function f using the PAR-DDH-based punctured PRF. Again, I'll go to this construction later, but assuming we have this primitive, how do we do modular arithmetic garbling? So first, the evaluator sums up its shares, E1 and E2, just over the integers, no modular reduction. Then the parties add up their keys and labels, mod P. Then they use the transform and multiply gadget, where the evaluator inputs the integer sum E star, the garbler inputs delta, and they input K star and L star respectively. And now they get some shares, ZG and ZE. So what I want to argue is that ZG and ZE are actually shares of delta times E star mod B. And the function we're going to use for the transform and multiply gadget is just reduction mod B. So first, we need to make sure the invariant holds, which is the parties K star and L star actually are shares of delta times E star. But this is easy to see because E star is just the sum over the integers. So K star plus L star is actually going to be equal to delta times E star mod P. And because this is true, the output from the guarantee of transform and multiply gadget, the correctness guarantee, what we get is delta times E1 plus E2 mod B. Good. So we have the Garbler gets ZG, the evaluator gets ZE, where they are shares of delta times E1 plus E2 mod B. And now what the Garbler and evaluator do is they just reduce, they just actually now sum the actual shares of the secret mod B, and then they compute their labels and keys as as the shares output by the transform and multiply gadget mod P. So let me just quickly argue that I actually think why this satisfies the invariant. So okay, for the shares of the secret, like before, just it's linear in mod B, so we satisfy the invariant. For the K3 and L3, like we just saw, it's equal to ZG plus ZE mod P. And because of the transformation that we applied, we have a mod B inside. And now we are actually computing over two different moduli. And E1 plus E2 mod B is nothing but E3. So we get delta times E3 mod B. And we've now satisfied our invariant. Both are invariants. It requires a little bit more effort, but it's not too hard to show that the transform and multiply gadget actually is enough for evaluating multiplication gates too. So putting everything together, we use this transform and multiply gadget, we garble the scheme, all the messages of the gadget are included as part of the garbled circuit. Now what is the rate? So every time we want to maintain the invariant for an addition or multiplication gate, we make a constant number of invocations to the transform and multiply gadgets. Each gadget invocation requires lambda bits of communication from the garbler to the evaluator, which means our rate is log B over lambda. Okay, so in the time that I have left, let me go over how we construct the transform and multiply gadget. So this is the transform and multiply gadget. I've just rewritten the primitive. And now I'm going to assume I have a punctured PRF, which again we construct using the PAR-DDH-based PRF, where the garbler can use its share KY to locally go from KY, non-interactively go from KY to a PRF key K. And the evaluator can use its share to compute a punctured key, K sub Y, which allows evaluating the PRF on all inputs except at Y. And that's why it's punctured. It doesn't allow evaluating at Y. So let's assume we have this. How do you evaluate the transform and multiply gadget? So this is a technique that was first introduced in the context of oblivious transfer by Roy, and then later adapted in the garbling setting by Heath, Kolesnikov, and Ng, where basically we use the garbler first converts its share to the PRF key. It then computes a mask A, which is the sum of the PRF evaluations over from Z to B. And it computes its share as f of I times the PRF evaluations. It then sends its input x masked by A. And then the evaluator computes this large sum. Essentially, what they're doing is they're computing, so since they know y, it's their input, they're computing f of y minus f of I. They're shifting each value of I by f of y, multiplying it with the PRF key, but they only have the punctured key, so they're going to evaluate it at using the punctured key. And the index over which they're computing does not include y anymore, because they can't evaluate the PRF at y. And then they add this f of y times x minus a as an additional final shift. So my argument is that the first sum there is equal to the second sum, where I've just replaced the punctured key with the PRF key, and I'm summing over all values. And this is because when I is equal to y, both terms are 0. And when I is not equal to y, the punctured PRF evaluation is equal to the PRF evaluation. And then with a little bit of symbol pushing, we basically get that the garbler and evaluator have shares of x times f of y, which is exactly what we wanted. And because A includes the punctured point, PRF evaluated at y, x remains private. Okay, the final component I need to show is the PAR-DDH-based punctured PRF, which is one of the main contributions. So the PAR-DDH-based PPRF has a CRS, which essentially consists of the pars of a random group element and a random exponent. So we have h to the alpha minus b to h to the alpha to the b, except we don't give h. So we have a hole in the middle where we don't give h to the alpha to the 0, or we don't give h, and we give everything else. And under the par DDH assumption, h is pseudo-random, right? An adversary should not be able to guess what h should be. And we set the master secret key to be the exponent alpha. Now, to generate a PRF key, we just simply sample a random exponent. And to evaluate, we compute h to the k times alpha to the x, right? And the evaluator the PRF key consists of the random k itself as well as the master secret key, so this is easy to evaluate. So let me just write down how the inputs and outputs look like. Essentially, we map, for example, 2 to h to the k times alpha squared, right? To puncture the key, what we do is we shift the key multiplicatively by a factor of alpha times y, where y is the punctured point. And to evaluate the punctured key, because there is a shift, we have to unshift in the CRS and then exponentiate. So let me just demonstrate this visually. So for an example, let's just consider we want to puncture at the third point. So the punctured key would be alpha cube times k. This means that when we exponentiate, for example, with h to the alpha minus 3, because the punctured key is already shifted by alpha to the 3, we end up with h to the k. Similarly, when you take h to the alpha to the minus 2, we end up with h to the k to the alpha power 1, and so on. And what's important here is that because the CRS has a hole, it does not have h, the evaluator or the punctured key does not allow computing h to the k to the alpha cube, and because the hole is pseudorandom, which means that that value is pseudorandom to anyone with the punctured key, and so we have security of the punctured PRF. Okay, so the last thing that I want to argue is that parties can non-interactively go from their shares to the PRF key and punctured PRF key. So let me just quickly show why this is true. So this is the correlated input that parties had. So what we do is we let G be the generator of ZQ star, where Q is the order of the group that we're working over, the par DDH hard group. And we set alpha to be G to the delta, right? So delta is simply the exponent, or the exponent to which the generator should be raised so that we get alpha. And now let's say parties have the correlated input of delta times y. And we need to show how parties can compute, the evaluator can compute a punctured key at y, and the garbler can compute a PRF key. So P here will correspond to Q minus 1. Again, we are free to choose P and delta however we want, because before we never assumed that, we never set it. We assumed it was given by the multiplication gadget, and here we are constructing the multiplication gadget. So what the garbler does is it takes ky, and to compute the PRF key, it simply computes G to the minus ky. The evaluator, on the other hand, computes the punctured key k sub y as G to the Ly. And again, with some, because they're shares of delta times y, what we end up with is the evaluator ends up with alpha to the y times k, which is exactly what we wanted. So we have the evaluator gets the punctured key. So do I have time for? Okay. So some concluding remarks. So handling multiplication gate requires composing the transform and multiply gadget. So we have to be a bit careful about bounding the output share size and ensuring privacy. So this requires some new techniques. Using the same delta for all wire values actually requires circular security. So we have to do some sort of key switching at every step. And finally, this construction naturally extends to a large polynomial ring, as long as the modulus is a smooth integer. Some immediate open questions are if it's possible to go beyond log lambda by lambda, improve arithmetic garbling beyond log lambda by lambda for modular arithmetic. And personally, I think it's interesting to see if we can go beyond 1 over lambda for the case of super polynomial size integer rings. And thank you. That's all.
Thank you very much. Do we have any questions? Now is your chance. Well, if not, I have one.
Yeah.
You're looking here at a selectively secure garbling scheme, right?
Sorry?
You're looking at selective security here, right?
Yes, selective security.
Have you considered adaptive security?
Yeah, that's a good question. So adaptive security requires, like even in the Boolean case, I think requires some new techniques because you need to be able to equivocate the garbled circuit later on. I'm not so sure if those techniques should translate directly, or I guess the question is about efficiency. So can we get it efficiently, and how the existing techniques in Boolean setting, what effect do they have on efficiency? I don't know off the top of my head. That's an interesting question, yeah.
Fair enough. Thank you very much.
Thank you.
Then let's thank the speaker again. And now our next talk is going to tell us more about adaptive security, but this time about free XOR in the plane model. And Khan is going to give the talk.
Yes, so hello, everyone. Is the microphone well? Yes, works well. This one, okay, I can use. Perfect. So this also works here, or no? Looks like that, okay. Yeah, this is joint work with Anu Achaya and Chetan Kamat. And yeah, let's first parse the title. So we are in a garbling session. This is again a talk about garbling, so I will not introduce garbling any further. But this talk is about a specific optimization technique for garbling, which is free XOR, which is a common technique for practical schemes. We have also seen this already in the very first talk today. It is in particular a key ingredient for half-gate scheme. And yeah, in this talk, we want to talk about adaptive security in the standard model. Adaptive security is required whenever we want to do the expensive circuit garbling in an offline pre-computation phase before we even know the input. Usually, it's notoriously hard to obtain adaptive security, and we have much better bounds for selective security. Most work, for that reason, focuses on selective security first. Also, in this talk, unfortunately, we show negative results. So we show limitations on provable security for free XOR-based garbling schemes in the standard model. So yeah, let's first talk about Yao scheme, then how Yao scheme can be optimized using free XOR-based garbling, and this is actually the scheme that we will consider in this talk. So to garble a circuit in Yao scheme, first, for each wire in the circuit, one samples two uniformly random independent keys. For each gate in the circuit, one computes 4 double encryptions, one for each possible input key pair, encrypting the respective output key. And the garbled circuit then consists of all these garbling tables. I guess you're all familiar with that, where each of these garbling tables, the ciphertexts within a garbling table, are randomly permuted so that the order of the ciphertext does not leak which key corresponds to which bit. And the encoding information then consists of all these input key pairs. So all this can be done in an offline pre-computation phase independent of the input. Then for an input X, the garbled input consists of the respective input keys. And in order to evaluate, there's also an output mapping that allows to map output keys to output bits. So evaluation works as follows. For each input wire, one holds one key that allows to decrypt exactly one of the 4 double encryptions, learn exactly one of the output keys, and this can then be mapped to the corresponding bit. The idea for free XOR now, yeah, we have seen this in the first talk already, is to set the key X1 to be a fixed global shift of X0. So we sample, instead of sampling all the K1s uniformly at random, we sample a uniformly random string delta and compute X1 as K0 XOR delta. Furthermore, for XOR gates, so if a wire is an output wire of an XOR gate, then we set the 0 key to be the XOR of the 2 input keys associated with the 0 bit. And this now allows to garble XOR gates for free. So for evaluating, we do not need any additional information. So there's no cost involved in garbling XOR gates. And evaluation just works by XORing the 2 input keys. This technique was analyzed by Applebaum, but only for selective security. And yeah, Applebaum considered exactly this scheme. So AND gates are still garbled as in Yao scheme, and yeah, XOR is for free. As mentioned in the beginning already, half-gates also uses this free XOR technique. However, they use further optimizations. In fact, they rely on a very specific encryption scheme that relies on a very specific hash function that has a very strong security property. So half-gates actually relies on the security of that hash function. Our results apply to both schemes, but in this talk, we will focus on the simpler scheme, so the free XOR optimization of Yao scheme. So what do we actually mean by security? So usually we have strong simulation-based security, but in this work we focus on a weaker notion of security, and since we show impossibility results, this only gives a stronger result. So we consider this weak notion of security, that is selective indistinguishability, where in the security game, the adversary can choose a circuit, can choose two inputs, in response receives the garbling of the circuit, the garbling of one of the two inputs, and has to decide which of the two inputs was garbled. However, in the standard application of garbling, we usually want to do this expensive circuit garbling ahead of time in a pre-computation phase. And to guarantee security in this scenario, we actually need strong adaptive security, where the input is actually chosen after the circuit was garbled, and that means it could even rely on the garbled circuit. So let me briefly recall what we know about security of Yao's garbling, and then go into what we know about free XOR-based garbling and what our results are. So Lindell and Pincus were the first to formally analyze security of Yao's scheme. They proved selective security based on INSI-based security of the underlying encryption scheme. You can always obtain adaptive security from selective security through so-called complexity leveraging or guessing all the adversarial choices, but in this case, this leads to an exponential loss in security, exponential in the input length. Jaffargoli and Wicks, they showed that actually one can get adaptive security at a loss that is exponential only in the depth of the circuit, or more precisely, the pebbling complexity, but for this talk, let's just focus on the depth. So this means, for example, for NC1 circuits, so for circuits of log depth, they had a polynomial reduction. Unfortunately, we proved this cannot be extended to arbitrary depth circuits. So me, together with Chetan Kamat, Krzysztof Pieczek, and Daniel Wicks, we proved that any black box reduction will suffer from a loss that is exponential in square root of the depth. So this is what we know for Yao's scheme. For free XOR, it's not very surprising that we need to rely on a stronger security notion, because we have this dependency of keys. We have only this one single global offset that is the only secret. It's not very surprising we need a stronger security notion, and the right security notion to analyze this was defined by Applebaum. It's a combination of key-dependent message security and related key security under linear relations. He also showed that this can be instantiated in the standard model from standard assumptions. For half-gates, this has further optimizations. Security relies on the security of the hash function. There was a new security notion called circular correlation robustness introduced by Choi et al., which suffices to prove selective security. However, it's a very strong assumption where we do not know how to instantiate it in the standard model. Jaffargoli and Oechsner already they were the first one to analyze adaptive security for free XOR, and they argued that pebbling techniques as used in Yao's scheme will not be very useful in this setting. And the reason for that is that now we have this one single global offset, which means we have to make a global security argument and cannot have a local argument like what we use in pebbling techniques. There's also two further recent papers on ePrint that I have to mention. They prove adaptive security for half-gates, but in a random oracle or random permutation model. In this work, we prove that any black box reduction that proves adaptive security of free XOR based on Lin RKKDM security of the symmetric encryption scheme will involve an exponential loss in security. And to compare this result, for Yao, we had actually polynomial reduction for NC1 circuits at least. This result applies even to NC1 circuits. Even to constant depth circuits, it would apply. So it's a much stronger limitation. Also, it is from a much stronger basic assumption. It holds for a very weak notion of security. Since it's a lower bound, it also applies to simulation-based security, so also stronger security notions are affected. It holds, so a similar result we get for half gates when we try to base security on circular correlation robustness of the hash function. So what does this mean? This basically means either we come up with completely novel non-black box techniques to prove security, or security proofs via random guessing, via complexity leveraging is actually best we can do, which leads to an exponential loss in the input length. So in the remaining minutes, let's talk a bit about the proof techniques that we use. We use oracle separation techniques, which means we define an inefficient ideal encryption scheme where the encryption function is simply a random injective expanding function. The adversary, on the other hand, is also an inefficient adversary that can break the scheme also by brute force breaking, brute force. And it can also break the garbling scheme simply by breaking the underlying encryption scheme. At the same time, we have to be careful how to define this adversary because it must not be useful to break the underlying encryption scheme. So as an image, how does the setting look like? We consider polynomial time reductions that have oracle access to those inefficient encryption and decryption procedures as well as the adversary A. And the goal of the reduction is to break lin RKKDM security of the encryption scheme. So far I have not defined exactly what this means. Here's the security game. For lin RKKDM security, the reduction has oracle access to either a real oracle or an ideal oracle, both parameterized by a secret key k. And it can send linear relations phi and psi, and in response, either receives an encryption of psi of k, this secret key k here, under phi of k, or an encryption of the zero string under phi of k. And the goal of the reduction is to distinguish these two cases. So first of all, let's define the adversary A more precisely, which means we have to define the circuit C, we have to decide how to sample x0 and x1, and how the adversary can actually break the garbling scheme. So for the circuit C, we choose the following circuit. On the first layer, there's only AND gates. All the remaining are XOR gates. It's a very simple circuit of logarithmic depth. Then, in response, we receive the garbling. This garbling contains now a garbling table for each of the AND gates. Now, after receiving C tilde, the adversary samples x0 and x1, basically uniformly at random, where clearly you have to be careful a bit if you want to cover also rewinding reductions. The randomness is somewhat extracted from C tilde, but I don't want to go into details here. And then, after receipt of x tilde, it has to decide to output 0 or 1. And it does so by checking whether C tilde is well-formed. So this is actually what is inefficient. And whether C tilde x tilde is consistent with this uniformly random x1 that it sent. So how to do these checks precisely, we will discuss now. If you look at an AND gates are asymmetric, so the output table is asymmetric. There's 3 times the same key encrypted and once a different key encrypted. And since we defined this encryption function to be an injection, that means for every ciphertext, there exists a unique key and a unique message associated with it. So an inefficient adversary can simply extract this message and this key. So given those ciphertexts, it can extract the messages, can check whether 3 times the same key was encrypted, assign this key to 0, and once a different key was encrypted, and this it assigns to 1. So this is about the output keys. It can also extract the encryption keys. It will check whether this has the correct pattern, and will assign the 2 keys that were, involved in encrypting the 1 key. It will assign the bit 1, and the other key is the bit 0. So this means, given C tilde alone, independent of the garbled input, there's a mapping from keys to bits that the reduction already committed to. And this is what we want to use for the security proof. The adversary can then check whether this input x tilde is actually consistent with this mapping, whether it received exactly those keys it should receive according to the bits in x1. So why is this adversary not useful? So first of all, the reduction in some, it can have many interactions with A, but in some interaction, it has to embed a challenge, which means it has to embed a ciphertext, a LIN-RKKDM challenge ciphertext within C tilde. Furthermore, our encryption scheme is a random expanding function, which means the set of ciphertext is sparse in the output range. So it's actually hard to even find a ciphertext without having queried the oracles. And this means in order for this adversary not to reject this ciphertext, this circuit, and output always 0, the reduction has to embed only ciphertext within C tilde that it derived through oracle queries. But for both types of oracle queries, either it knows the key and the message for this type of oracle queries, or it knows the relation to the secret challenge key. And there's only this one secret challenge key. So if we go back to free XOR, how things are garbled, the only secret is this delta, the secret global offset. And all ciphertexts have been derived through oracle queries. And this allows us then to prove that C tilde, X tilde will be considered malformed with respect to X1, or from the oracle queries alone, one can already extract delta. Why does this not contradict selective security? Well, there's one case that happens with negligible probability, namely that the reduction manages to embed the LIN-RKKDM challenge key exactly as this secret delta, and consistently with X1. But since it has to do the embedding before it actually knows X1, this is exponentially unlikely to happen and requires to correctly guess X1. So to conclude, in this talk, we proved that while free XOR is selectively secure, we cannot prove it adaptively secure using standard proof techniques. This does not mean that we have an attack. It also doesn't mean we have a counterexample at the moment, but it does show some weaknesses of this scheme that are significantly stronger than the weaknesses we could show for Yao's scheme. Yeah, let me thank you. I'm happy to answer any questions.
Thank you very much. Do we have any questions? No, everybody's shy today. I do have a question. How pessimistic are you about proving free XOR adaptively secure? Do you think there is a way?
I actually rather think we could construct counterexamples, so not from these assumptions. This is what I believe at the moment. I would believe one could find contrived examples. This does not apply well to the actual schemes that are used in practice. But I'm rather pessimistic regarding that, but maybe one could find a change in the scheme or even stronger assumptions. Unfortunately, Half-Gates already has a super strong assumption that we don't even know how to instantiate in the standard model, so I'm rather pessimistic.
Okay, fair enough, thank you. Let's thank the speaker again.
Thank you.
And we have one last talk on the session. And that's by Marian, who's going to tell us about tiny labels and how to compress garbled circuit input labels efficiently.
Yeah, thank you. So I'm going to present this paper on tiny labels, a joint work together with Hanjun and Rachel from the University of Washington. But this is not at all going to be about I/O. In fact, I'm going to try to convince you that label compression is something that lies on the other end of the cryptographic spectrum, that we can actually instantiate it concretely, efficiently today. And so first of all, thank you all for still sticking around for the last talk of the conference. I know everyone must be really tired, so I'll try to keep things as light as possible. So yeah, first of all, a garbling scheme. In the context of this work, we're always going to assume there's public Boolean circuit, such as this one. But we don't really need to look inside at the gate of this circuit. We're just calling it a circuit C with the input X and output Z. All right, and we can take the circuit, we can garble it, and what we obtain is something that we call a garbled circuit, C hat. We can imagine it as this blob right here, which doesn't take bits as input anymore, but keys of length lambda. So the garbler would assign 2 keys to each of the input wires, one corresponding to 0, one corresponding to 1, but they are indistinguishable from each other. And now what you can still do if you have the garbled circuit, as well as a set of input labels, meaning that you have one out of the 2 keys for each of the input wires, then you can still evaluate the circuit and obtain the same outcome as in the normal circuit C. So security would just state that you, from the garbled circuit as well as the input labels, you don't learn anything except the desired outcome C of X. All right, the most common application of this is probably two-party computation. I want to get back to this later, but I want to say that garbled circuits are actually much more powerful than that. They have a lot of other applications. So for example, what we can do with them is to outsource computation on sensitive data. So let's look at this setting right here. Alice is going to embark on some journey where she's going to collect some sensitive data X, and she's only going to have limited resources, meaning that she doesn't have a lot of computational power and not a lot of bandwidth for communicating with Bob. Now, she still wants Bob to learn some analysis C of X of her data, and in order to make this feasible, she's allowed to engage in some kind of offline phase with Bob before she leaves for her journey, where she has enough resources and the circuit C is already known. Now, using garbled circuit, what she can just do is garble C, send the garbled circuit to Bob, and then in the online phase, the only thing left to do is for her to send the input labels to Bob. Now, what we really try to optimize in this setting is the size of the input labels, right? So in the naive case, that would be just size of the input multiplied with lambda. But in 2013, Applebaum et al. Have shown that we can actually do much better. We can somehow compress these input labels. What we need for that is to increase somehow the offline communication, which we here denote by some kind of ciphertext that depends on the keys X. But if we allow that, then the compressed input labels can actually be, we can get them down to size just input length plus a polynomial in lambda, so there's no multiplicative factor of lambda anymore. All right, and this is also actually optimal as they've shown in the same work. So AAKW was basically the first work to study this label compression problem. They've proposed a couple of different schemes, the most efficient one probably being the RSA-based scheme, where the additive overhead is simply a single RSA group element. But it also comes at the cost of significant offline communication. Now, there's been a couple more recent works that try to weaken the assumptions a bit, but they're practically not really relevant. And another very recent work that has introduced the notion of projective PRGs, which can also be used to construct label compression. And they also proposed an RSA-based scheme similar to the original one with the same online communication, and they actually somehow achieved to get the offline communication entirely free. Now, it sounds like that might be a satisfying solution to the label compression problem, right? We have optimal offline communication, optimal online communication. But if we look at the computational cost, things actually look very different. So to decompress just a single input label, you need to perform log of input size RSA exponentiations. And if we just have a medium-sized input of length, let's say 100,000, this would take around 30 minutes. Comparing this with the naive version of just sending all of the input labels naively in the online phase, if we even have a very low bandwidth of, say, 1 megabit per second, it would only require 13 seconds. So that's what we try to address with our work. We want to try to compress labels in such a way that we outperform the naive solution, both in terms of online communication and computational cost for decompressing the input labels. So we propose tiny labels based on the ring LW assumption. The most efficient version of it also requires the Random Oracle model. And online communication is again optimal. The additive overhead is simply a single ring element. And offline communication, well, it's not entirely free. We do have offline communication, but we observe that we can reuse it for as many garbled circuits as we want, and therefore its cost actually amortizes towards 0. But the most interesting thing is the computational cost, because for each batch of n input labels that we want to decompress, where n is the degree of the ring, we only need to perform log x ring multiplications. Now, we actually implemented this, and on input of length 100,000, it would actually take less than 1 second. All right, before going a bit into our construction, I also want to give another application of label compression that we propose in our paper. And for that, we actually go back to the setting of two-party computation. So let's say Alice has some secret input X, and Bob has some secret input Y, and they know that they somehow want to analyze their data together. They just don't yet know how the circuit C is going to look like. And the observation is that we can actually use label compression in order to kind of pre-process the garbled circuit without knowing how C looks like. And then once C is available, only a very small amount of data needs to be sent from Alice to Bob. So what we need in order to achieve that is a universal circuit. It takes a bit description of another circuit C as input, as well as inputs X and Y, and it outputs C applied to X and Y. Right? Normally, two-party computation based on garbled circuits roughly looks like this. Alice just garbles the circuit, sends C hat to Bob. Now, they also somehow need to communicate the input labels corresponding to both Alice's input and Bob's input. But in this setting, we are actually interested in minimizing the size of the garbled circuit itself, which naively would have sized roughly a number of gates in C times lambda. But using the universal circuit combined with label compression, we can split it in an offline and an online phase, where in the offline phase, Alice just sends the garbling of a universal circuit, and in the online phase, the only thing left to do is to send the compressed input labels corresponding to the circuit C. And using tiny labels, this is just going to have size polylambda. So this can actually be seen as some form of succinct garbling, right, with only polylambda size in the online phase, except that it comes at the cost of an offline phase. But this does not depend on anything, not on the circuit C, not on the inputs X and Y. Now let me tell you a bit about how we achieve all of that. Our main tool is what we call batch select, which you can see as some form of functional encryption scheme. So suppose there's a sender who has two message vectors, M1 and M2, over the integers modulo P, and these vectors have dimension W. Now, the sender can encrypt both of these messages in order to obtain the two ciphertexts, and once the sender also has a selection vector from the same space, they can compute a secret key SKX. Sending all of this to the receiver, what the receiver can now compute is this evaluation term right here. The component-wise multiplication between M1 plus the second message vector M2. The reason for doing all of this and not just sending this evaluation term directly from the sender to the receiver is, of course, that you can first send both of the ciphertexts without knowing X, and then once X is known, only a very succinct key of size polylambda needs to be sent. Now, I also should mention that the receiver, in addition, needs to know the selection vector X in the clear. So simulation security actually states that the receiver doesn't learn anything from the ciphertext and the secret key except the desired evaluation outcome, as well as the selection vector that is supposed to be public. And this tool can be applied almost immediately towards the label compression problem, because component-wise multiplication is exactly what we need. So suppose Alice has just garbled some circuit with input keys K0 and K1. So K1 is the vector consisting of all the keys corresponding to input all 0, and K1 is the vector consisting of all the input keys corresponding to input all 1. Now usually those would be lambda bit strings, and we just embed them into the integers modulo P. And then in the first step, Alice encrypts the vector K1 minus K0, and then encrypts K0. Now, once she knows what the input X to the circuit looks like, which is a bit string of length W, she just treats this vector as the selection vector and obtains the secret key SKX from it. And then now we can see what Bob is going to learn. Exactly this evaluation term right here, which turns out to be the set of input labels that Bob needs in order to evaluate the garbled circuit on input X. Okay, so the two ciphertext is what we would regard as the offline communication in the context of label compression, and SKX is what we would call the online communication, which, if we use our instantiation of batch select, is just a single ring element. Now, in the beginning, I said that the minimum required online communication is length of input plus polylambda, so where did the length of input go to? Well, Bob still needs to know the input X in the clear, right, in order to run batch select decryption. And therefore, if Alice doesn't want to reveal her input X to Bob, she actually needs to one-time pad this and send the one-time padded version to Bob, who can then remove this one-time pad basically in the first step of the garbled circuit. So the online communication would be length of input plus a polylambda. Offline communication, well, it's not entirely free. It has an overhead of log W on top of the size of the plain text. Now, earlier I did tell you that offline communication would be essentially free. So how do we achieve that? We need to apply two different optimizations to the ciphertext CD1 and CD2. And the interesting thing for that is that you don't even need to know how batch select is implemented in order to see how these optimizations work. So first of all, let's look at CD1. Usually, in a practical garbling scheme, you would use the free XOR assumption, right, as you've seen, for example, in the previous talk. So you wouldn't sample both the vectors k0 and k1 as uniformly random, but instead you would choose one fixed offset delta and use this for the difference between all of the key pairs in the input, right? So then the term that Alice wants to encrypt in the first step simplifies to simply a vector consisting of W times the same fixed offset delta. And now our observation is that we can take this one step further. We are not restricted to using this value delta only for a single garbled circuit, but we can just reuse it for as many garbled circuits as we want. Right? So if the batch select supports a correspondingly stronger security notion, we can actually just reuse this ciphertext CD1 for as many garbled circuits as we want, and therefore its cost amortizes towards 0 when doing this often enough. So what about CD2? Here, the observation is that K0 is simply going to be a uniformly random vector. In our construction of batch select, that also means that the ciphertext CD2 is going to look like a uniformly random vector. And now the thing that we can do is that we don't sample K0 first and then compute the ciphertext CD2 from it, but we just do it the other way around. We sample the ciphertext CD2 first, and then reversely compute the inputs K0 from it. All right? And sampling CD2 is something that we can do using the random oracle. So Alice and Bob both just have some short seed, put it into the random oracle, and both obtain this long ciphertext CD2, which does not need to be sent to Bob anymore, but it's really just a short seed of length lambda. All right, that's basically how we obtain label compression. And now I just want to give a very, very high-level overview about how we get batch select from ring LWE in a concretely efficient way. So let's just compare it with what we get from linearly homomorphic encryption, or LHE. So on the right-hand side, you can see the thing that we want the receiver to get from the batch select decryption, right? It's some kind of encrypted message vector M1, component-wise multiplied with the public vector X. Comparing this with LHE, what we can actually easily get using a simple LHE scheme from ring LWE is the multiplication between an encrypted message vector M1 and a public scalar X. So the main question is kind of how do we bridge this gap between these two things? And for that, we introduce another primitive that we call a link. The techniques are heavily inspired from a recent paper by Döttling et al. That constructs laconic encryption. And this primitive actually allows the receiver to get something like this component-wise multiplication, except that it comes at the cost of a non-succinct secret key. So why is this still an interesting thing to study? Well, the secret key is going to have a very special format like this. So the whole picture looks like this. Alice encrypts M1 first using a-link, sends the ciphertext to Bob, and Bob, given any vector X of his choosing, can compute this evaluation term right here that involves the component-wise multiplication that he wants, except that it's hidden using this secret key of special format, R times dx. And R is just a secret vector that Alice got out of this a-link encryption, and dx is going to be some publicly computable scalar given the public input X. And so, yeah, we have now a vector scalar multiplication between a secret vector and a public scalar. So for that, we can just use LHE, right? Alice just encrypts the vector R using LHE, sends the ciphertext to Bob, and then once she also knows the input X, she computes the public digest dx and gives to Bob the secret key skdx that he can then use in order to obtain r times dx. Now for batch select, we also need to ensure that we add the second message vector m2 on top of all of this. But that's actually pretty easy because everything in here is linear. We can just put m2 into the LHE encryption as well. And in the end, Bob gets m1 times x plus m2. All right, so that's really just a very high-level description. So for example, I ignored all the ring LWE noise that we get in here. And in our paper, we also propose a couple of different schemes depending on whether you're willing to use the ring numerical and how large your ring LWE modulus you want to have. Now I want to end with two open questions. First of all, now we've seen some kind of practical label compression from ring LWE. We do know that we can also get label compression from a bunch of other assumptions, but we don't really have any practical schemes there yet. And the second question, well, that's a really large open question. Can we get succinct garbling that is actually practical? In this work, we've seen some kind of succinct garbling that could perhaps be practical, but however, we relaxed the notion a little bit by allowing this offline phase where we send the garbling of the universal circuit. All right, thank you.
Thank you very much. Do we have any questions? Okay, then I have a question. You mentioned using universal circuits.
Sure.
How much of a efficiency loss do you have from that? I mean, a universal circuit is bigger than your circuit.
Yeah, sure. So we didn't implement this universal circuit itself. We only implemented the label compression step by itself.
You haven't tried it out?
We haven't implemented it with universal circuits.
Right.
We have implemented the label compression stuff, so that's something you can definitely do. And for this universal circuit, all right, here we have it. Well, you can't build universal circuits with an overhead of, I don't know, 4.5 times log of the size of the circuit. Right?
Okay.
That's, I think, the best you can do.
Thank you very much. Any other questions? Somebody got excited? No, then let's thank the speaker again. And let's thank all the speakers of the session again.